Welcome to a little primer on the FFT. We're going to do this as a series, and today we'll just get our feet wet. So this will be FFT number 1, and we'll go through the steps of creating an effects processing routine using Max's PFFT object, which we'll explain here in just a moment. So the process we're going to create today in Max is going to be a spectral noise reducer. We could say spectral noise reduction. So an example where you might want that is you have some sort of recording that has like blowers running in the background or some other sound source that you want to eliminate everything but the important stuff. We can simulate that here. We're going to have a noise object. Then we could have a saw oscillator here. And we could mix these two together in some proportion. So we could just say that the noise is going to be making up a little bit of our sound source. We'll let the saw make up the other part of the sound source. And we can randomly generate the saw frequencies, which will be what we hook up here. So we'll just have a metro running, and we'll say, every of the metro running, and we'll have it beat out at quarter notes. We'll go ahead and turn it on by default. Give ourselves a little visual. We'll generate a random number. We can say that it's going to be in a MIDI range. We'll just use the M to F. Convert it to a frequency with a little bit of a slide to it. We can portamento around. Add these together, and we'll have our simulated recording. I always like to put a gain control on the end here. All right, let's take a listen. We need to start the transport. We can go to extras, global transport, and then go ahead and activate it. There we go. Okay, so here there's a broadband noise and there's a frequency, which is the content we're actually interested in. So I'm going to go ahead. I'll encapsulate all of this here into a subpatcher, which we can call simulated noisy recording. All right. So that'll feed our process that we're about to create. And that process is going to be executed using the PFFT object. PFFT is like a poly object, so it won't create this unless I tell it that we have a patcher that we're going to point it to. Inside of that patcher, we will be doing FFT processing, which is to say that we're going to be processing the signal in a spectral domain or in a frequency domain. So in order to do this, I need to create that new patcher. So here we go. I'm going to create a new patcher. FFT patchers, PFFT patchers, use special inlets for their input. So where a poly object would use an in tilde, PFFT patcher will use an FFT in tilde, and we need to give it a number that will tell us if is this the first inlet, which it is, or is it a second inlet or a third inlet. So there's our FFT in 1. And we can have an FFT out for our output. This is similar to the out tilde object in poly. And again, this will be the first outlet. So if we want to create the simplest possible patcher, we'll pass the inputs to the outputs. The FFT in will take a single signal as its input when we load it up in a PFFT, and it produces two different outputs. These are known as the real signal and the imaginary signal, which are two components of a complex number. So let's go ahead, we'll save this patcher, and we're going to save this one. I'm just going to put it on my desktop. We'll call it noise reduction. At the moment, it's not doing noise reduction. It's just passing the real and the imaginary signals from the input to the output. So now I can come over here. Let me go ahead and save this, which is going to be FFT part 1. Okay, now in our PFFT, I can go ahead and load up our noise reduction max patcher. If I double click on it, you'll see, sure enough, here it is. And if we pass the input to the output, we'll go ahead and turn it on, and we'll hear the same thing we heard before. All right, we want to get rid of that noise. Here we are in our noise reduction patcher. I just double click this to get to it. I can click modify read only and then unlock it. That saves me the having to go back to the disk to open it manually. So the question then becomes, what do we want to do in here? What really in here is happening? So we need to talk a little bit about what the FFT is doing. I'll go ahead and close this for just a moment. If we look at the PFFT object, we passed it the name of a patcher. We can see also that it needs another argument, which is the FFT size. The FFT size is going to define the frequency resolution that we get in the FFT. So, as a starting point, I could go ahead and say, I want it to be 512 samples. So what does it mean for this to have 512 samples? Well, it means that the FFT process is going to gather 512 samples, and once it has collected those 512 samples, it can do this fancy piece of math called the Fourier transform, and it will calculate a different set of 512 samples. That other set of 512 samples is what we see in this patcher, represented by this real and this imaginary signal. When we're operating inside this PFFT, we're then operating in a different sort of world. Whereas in typical MSP patching, we're in what we would call the time domain. Every single sample represents the next step in time. When we're inside this PFFT world, we're in a frequency domain, and that means that each consecutive sample doesn't represent the next step in time. It represents the next step upwards through a band of frequencies. So what we've done when we said 512, we said collect 512 samples in sequence in the time domain, and then we're given 512 frequency bands. And so each sample is going to be from 0 hertz all the way on up to our sample rate. So if we wanted to know how many bands or what frequencies are represented by these bands, we can take the current sample rate. So for example, if I take a DSP state object, it will produce for me the sample rate out of one of these outlets. Current sampling rate right there. Okay, we take that sample rate, we divide it by whatever our FFT size is, which is right here. So this is our sample rate, which I'll abbreviate with SR. And then this right here will be our FFT size. These are both in samples, okay? And then, so this is going to tell us the width of each frequency band in the FFT. So given this, then we know that as we step through back over here in the frequency domain, each time we get to the next sample, we're going to be looking at the next bin or the next band of roughly 86 hertz. So the this last outlet here on the FFT in is going to tell us the bin index number. So when this is 0, we're looking at 0 to 86 hertz with these two signals. When this says 1, then the numbers represented in these other two signals are going to be from 86 hertz up to 86 hertz times 2, which should be something like 172 hertz. Sometimes you'll really want to know what these bin numbers are, so you can treat each bin or each band in some different way from the other bands. In the case of this noise reduction algorithm, we just care about the content of each band. So we won't be using this particular feature of the FFT in object at this moment. We are using this real signal and this imaginary signal though. And so we have to come to terms with what they're producing. What they're producing, first of all, as we already indicated, they are not producing something that represents a sample in time. They're representing a bin. But they're representing a real and an imaginary component of a complex number. That doesn't necessarily help us to understand what's going on in the FFT. Quite often what we want to know is we want to know what is the magnitude or the phase of the content that's in that frequency band. For example, if you had a real-time analyzer, you would want to know, like, what are the volume levels in this band? Or if you were going to attenuate those volume levels, you'd need to know that. So to get the magnitude, there is an object that we can use here called the card pull object. We use the signal version of it. And if we hook this up, actually we can even look at the assistance for it, and it'll tell us we're going to hook up a real and an imaginary input to it, like so. And lo and behold, it's going to produce an amplitude and a phase, which is exactly what we want, and it's something that we can understand better. For this noise reduction algorithm, we want only the strong signal to come through and all that stuff in all the other bands to be attenuated. So what we can say is we can say, if this amplitude meets some threshold, then go ahead and let it through, and otherwise we want to quiet it. So our first most crude version of this, we can use a greater than tilde, and we can set the threshold at some arbitrary number. Okay, and so if it's greater than 0.25, it's going to produce a 1. Otherwise, it's going to produce a 0. And then we can go ahead and multiply the 1 or the 0 on the imaginary and on the real signals before sending them back out. I'll go ahead and save this, and then we'll come over and see if it does anything related to what we want. It doesn't necessarily sound like it. So it could be any number of things are wrong here. One of which could be that we don't have the right threshold chosen. So let's make it so we can change that threshold. Just like with the poly object, we can use an in object, which will define an inlet, and we'll say in, and then we'll give it 2 because this is going to be the second inlet. And then we can hook this up. Now we can control the threshold with this inlet. Save that, close it, try again. We need to reload our PFFT here also so that it is updated with our extra inlet. Go ahead and throw a float on there. Okay, now we're getting somewhere. Okay. So when we get into this range where it's kind of ambiguous, there's some artifacts we hear. Okay, but it does exactly what we want it to do. It may not be the cleanest sounding noise reduction algorithm in the world, but we just started, and there are a lot of subtle things we can do to improve this. Just to review once again, we're simply taking each band of these 512 bands, they're 86 hertz bands, and if there's not enough energy in that band, then we just go ahead and silence it. So that lower lying noise will get silenced. So that's our super cheap and easy noise reduction using the PFFT object and the power of this FFT, where we can process many bands of audio by working in this frequency domain. There's another example of something we can do with the PFFT. Scoot this guy over here. And that is, we could do equalization. So just imagine if we could have 512 bands of equalization, that would be pretty rad. And there is an example in the Max examples that you can look into called the Forbidden Planet. We'll just build up one here that's kind of cheap and easy all on our own. Instead of using a simulated noisy recording, we'll just go ahead and just use straight up noise. That'll demonstrate our equalizer pretty well. And we'll come over here, make another PFFT, and we'll go ahead and hook this up. Hack those out for now. Then we're going to make a new patcher. Our new patcher is going to have an FFT in, and it's going to have an FFT out. There we go, FFT in 1, FFT out 1. And then I'm going to save this. This one's going to be saved as FFT equalizer. Come here, we'll call it FFT equalizer. Okay, and if we hook this up again, similar to how we did the other one. We're just passing our bands through from the input to the output. When I come here and turn it on, we'll just hear noise. Sure enough. So what we're going to do for this equalizer is we need a lookup table for all of the bands that we're going to use. So we'll use a buffer object. That makes for a handy lookup table that we can use at signal rate. And we'll call it buffer EQ buffer, like so. Okay, and now we need to set the size of it, but we could say, you know, we're not sure what the sample rate's going to be. So if we don't know what the sample rate's going to be, we don't want to hard code the number of milliseconds long that buffer is. So we don't want to go typing that it's 11.6 milliseconds or something for 512 samples. That might not be accurate depending on the sample rate. So what we can do is we can send a size in SAMPS message to buffer, and we can do 512, change this to a load bang, and that will size our buffer to be 512 samples long, so that the lookup table is the same size as the number of bands that we want to have in the buffer. Okay, now right now the buffer has nothing in it at all, but that's fine. We can change that in a moment. So now we know we're going to have a buffer called myEQ buffer that we're going to use as a lookup table. If we come in to our frequency domain patcher, we use the index object. The other buffer reading objects all have various kinds of interpolation. We don't need interpolation in this case. We just want to look up the exact value in an exact bin or at an exact index. So we use this one. And then what's going to happen is this tells us, remember, what the bin number is. So 0 would be the first band of frequencies, 1 is the second band of frequencies, and onward. And this buffer will contain a bunch of those different values. Then we can apply those values to the real signal and the imaginary signal. Like so. That's really all there is to it. So now I'll save this. We'll come back here, we'll turn this on, and we'll hear silence because this buffer is filled with zeros, which means that at every single index a 0 is going to be multiplied. Sure enough, all we hear is zeros. So I'm going to create a peak object with the name of this buffer, and then I can send in pairs to turn on or off any certain bands I want. So if I wanted to make the 5th band come through at full power, we'll multiply the 5th band by 1 instead of by 0. Sure enough, we hear that. If we look at this buffer display here, we can see that. If I were to write 0.5, it would have that band at half strength. And then I could turn on another band. Let's come to band 10. We'll make it a little bit weaker. So I'm just using white noise right now. I could use any source to be EQing it like this with this like super high res filter. And we can see here in the buffer that that's exactly what's happening. So if we go ahead and, having seen that now, come to the file browser, we can pull up the Forbidden Planet. And if we take a look at this Forbidden Planet, we'll see, sure enough, we're seeing the same effect. This is controlling or filling a buffer. If we double click this PFFT, we can see that it's using a peak object to fill this EQ fun buffer down here, which was sized in samples, 512. And over here, we're multiplying using an index object. So there's another resource here for you to investigate, and there's a lot more for us to talk about with the FFT. But hopefully this helps you get your feet wet and will encourage you to start exploring. Happy patching!